All right, today we're going to be looking at a way to solve equilibrium problems called ice tables. And these are things you may have heard of before. They are ways to break down showing how a chemical reaction with some initial non-equilibrium condition will change to get to equilibrium. This is something we've looked at qualitatively, but ice tables are really going to break down how to quantitatively determine, well, these will be our new equilibrium concentrations. This amount is going to be consumed and created in solution. And while they may seem like a lot to put together at first, the whole purpose is to provide a mathematical form that we can use in our K expression that allows us to solve for these results. So let's take a look at how they get constructed. ICE stands for Initial Change Equilibrium. And breaking out a table like this is a way to show the change in the equilibrium for a reaction that is starting from an initial non-equilibrium state that changes to form an equilibrium position in the end. And we can do this by applying variables, which can help us solve for a more complex expression. Again, it's to break down this process of defining the change to get to equilibrium. So the most common time where we want to use an ICE table is a lot of times we only start with reactant, right? We're just starting a chemical reaction. It's an equilibrium reaction and we're forming product, but we don't have any of that to begin with. That is a great non-equilibrium state that we're starting with that has an initial and then changes. And so again, right, this can apply to a wide variety of situations where we start with a non-equilibrium mixture and we want to know where the reaction goes. This is a reaction that we've studied previously. If we start only with reactants, some will become products. But how do we determine how much product is formed based on its equilibrium constant? We know the information is there, but how do we get to that final calculation, right? This is what we're going to use an ICE table to solve for. So let's consider the following practice, right? And we will, as time goes on, start incorporating unknowns into our ICE tables and sort of solve for them in the very end. But for now, we're just going to work on piecing together parts of this ICE table. So here's our problem statement. And as we begin to form our ICE table, let's start with, as a header, our chemical reaction. We know that for each of these reactants or products, we start with an initial amount. We know that there's going to be a change, that is how much it changes to get to equilibrium. And we have a final equilibrium value, which is going to help us get Kc, right? So again, we know that K is only valid at equilibrium, so it's only with expressions for all three of these at equilibrium that we can enter them and either solve for Kc or use Kc to solve for what's in our ICE table. So the first thing I'm going to do here is put in what I know, right? What do I know based on this problem for my ICE table? And that is the following, right? We say that 3 moles of pure NaCl is placed in this flask and allowed to come to equilibrium, which implies that there's none of the products that are there to begin with. So because it's 3 moles in 2 liters, 1.5 molar NaCl, and none of the other 2 products. And additionally, it says that, well, after some time goes on, we know the concentration of the NO, the sodium or the nitrogen monoxide, and we have that concentration. So I'm going to go ahead and put that in here too. This is just applying the knowns from our problem, and I hope that that makes sense where all those values come from. When we're breaking down this table, equilibrium is just initial plus change. That is the definition. This whole table is trying to get to an expression for the equilibrium. And because we often think about our initial conditions and the change, we're going to break them out into those different cells in order to reach equilibrium. So how can we use this to solve this ICE table? Because if we get the equilibrium row, we're going to be able to calculate Kc, right? We need values for all 3 of these in equilibrium, and maybe we can use that to get Kc. So I recommend you pause here and see if this connection between the initial and the change to get equilibrium can be used to fill in a cell or two. Then maybe those cells can help fill more in, because remember that if the reaction is shifting a certain way, everything needs to be created or consumed in relationship with one another. This is a recipe, right? And maybe that can help you get the rest of the way. So again, pause, give this a try, and then we will show the answer. All right, I hope you've been able to give it a bit of a chance here. So remember, this is sort of our initial setup for this ICE table. And the first thing I would look at is, well, we know that the the nitrogen monoxide goes from 0 molar to 0.25 molar. And that means that 0.25 molar has been formed. And because we know that 0.25 molar has been formed, we know that everything about this reaction is in relationship to that. So if we have this entry along the C row, the change, we can get the others as well. We know that if two NOs are formed, that two NOCLs must have been consumed. So in forming 0.250 molar, we have consumed 0.250 molar of the reactant. And finally, we also know that it forms 0.125 molar of the Cl2 because only one is formed for every two NO that are formed, therefore it's only half the value. But again, if we have one entry in this change row, we can get the whole thing because we know that these are all in proportion with one another in accordance with the balanced chemical reaction. Now that we have the change row for all of the different chemical species, we get equilibrium simply by adding I plus C, and we get the following. And these are the equilibrium concentrations for all three species. With this, we can use it to calculate K. We have all three at equilibrium, we plug them in, and we get the following here to find that K equals 0.0050. So again, I think that these ICE tables are a really good tool for breaking down how to solve a problem, and this particular problem has been solved as shown. Okay, so let's use K to get equilibrium concentrations in another example. And here we don't know the equilibrium concentration, but instead we know the value of K. Again, this is going to be the most common time that we're going to need to use an ICE table because these K values for reactions are well studied. They're tabulated and they're just able to be found for most cases. And if we know that the initial condition of something here like HCN in water is as shown, we should be able to know what happens when the reaction reaches equilibrium based on this K. Keep in mind that this is a very reactant-favored reaction where almost everything is going to be left as reactants because the value of K is so low. But there will be a very small but significant amount that goes from reactants to products. So let's see how to approach this. Make an ICE table, right? How do we fill in our ICE table? I might encourage you to pause here and see if you can set up your ICE table just to see how you're getting things going. Start with the initial row to show how much of each there is. There hasn't been anything said about how much product we start with, so the implication is 0. Start with that. Then for the C row, think about the shift. And if the shift makes sense, then the final row is just going to be I plus C. Okay, this is pretty challenging to do on your first time, so I hope that you gave it at least a little bit of a try, but this is what we should come up with, right? The initial HCN is 0.10. The water, it's a liquid. It doesn't show up in the equilibrium expression, so we don't really need to worry about it too much here. But as it shifts, know that water is being consumed, and then we get 0 for the Cn minus, 0 for the H3O plus. As this reaches equilibrium, some amount that we don't know yet, but some amount X of HCN will be consumed. We know that it has to be consumed as it shifts to the right, and as that amount is consumed, plus X and plus X for the Cn minus and the H3O plus. It's all in relationship to one another according to this balanced reaction that we get the change that occurs when we go to equilibrium. And finally, our equilibrium row. The change row is honestly the hardest one to define, so define that one. Make sure that you are getting coefficients that are the same as in the balanced chemical reaction. They're all 1 here, so it's a little easier, because once we have that, it's simply I plus C, 0.1 minus X for HCN, and X each for the two products. Now let's put these into K and solve for X. Again, once we have equilibrium, we just plug all of those right into what we know the K expression should be, which is the following, and we end up getting X squared over 0.1 minus X equals K, which we actually also have the value for. And so now we can solve, right? There's one unknown, it's one equation, and we can solve this. But the problem here is that this requires the quadratic formula. We're going to need to do a quadratic solving method in order to solve this. But actually we don't need to. We can use a mathematical approximation here to not compromise any of our precision while also sidestepping the need for the quadratic formula. And this is a very important assumption and method that you should learn how to use. It's an important part of this class. Okay, so here's the mathematical expression we need to solve. Here's our ICE table. Is X large or small, right? Well, if we knew that X was very small, for instance, then we might be able to approximate 0.10 minus X as pretty much just still 0.10 because X is so small that 0.10 minus X is still 0.10. And that's what we're going to do because K is so tiny. And if K is so tiny, we know the shift to the right is incredibly tiny. And if we know that shift to the right is incredibly tiny, then the concentrations of the products are incredibly tiny. So let's go ahead and do this, right? We say there's a really good chance that X is very, very, very small, so much that it's not going to effectively change this equilibrium concentration to the sig figs that we have, right? It's of course going to change it in a theoretical sense, but in a practical sense, let's call it 0.10 for now. And the tolerance that we're going to use is that if this X is less than 5% of the original value, so basically less than 0.005 in this case, then we're going to say that this is a fine approximation. And so with this approximation, we turn it into the following. X squared over 0.10 equals 6.2 times 10 to the negative 10, and we solve for X equals 7.9 times 10 to the negative 6. And indeed, this is really, really, really small. So because of this, we can say our correction works, our 5% rule is just fine, and this is acceptable, right? So because this value of X is so small, we can accept the implementation of the 5% rule that we did. We've simplified our math quite a bit, and very essentially, we need to, in the end, express our concentrations of the three species, which is what we wanted in the first place. They're just equal to X for the Cn minus and the H3O plus, but still we need to express them as concentrations, not in terms of X. And for HCN, well, we've kind of returned to our 5% rule assumption, 0.10 minus 7.9 times 10 to the negative 6. You know, this is going to be 0.09999 to quite a bit, and we can say that, well, to rounding, it's still 0.10. Our 5% rule was just fine to do here and simplified the math quite a lot. Okay, give this one a try, right? Here is a very similar problem. We're saying that we start off with a certain amount of N2O4, and we're going to do an equilibrium ice table problem with it. Go ahead and pause here, try to work through this one. You have Kc, you have the initial condition. Remember, there's no NO2 to start if it's not specified. So give it a try, and then we will walk through it. All right, hopefully you've been able to give this a good attempt and maybe even get an answer. We want to do an ice table, right? And initially, our concentration of N2O4 is 0.129 molar, NO2 is nothing. Here I've defined minus X over 2 for the N2O4 because for every one NO2 that forms, only half of an N2O4 is consumed. They have a 1:2 ratio. And if you ended up defining this as minus X and plus 2X, that's perfectly fine. We're going to take a look at how that works and gets us to the same answer in just a second. We define here our E rho, which is I plus C, and we say, well, it's a pretty small value of Kc. Maybe our 5% rule can work. Let's give it a try. And when we do that, we end up with the following. Here's Kc equals products over reactants. We plug in based on our 5% rule. We solve for X and we get 0.00117. And we say, well, is our assumption okay? Well, this value is quite a bit smaller than 0.129, and therefore I would say our assumption is just fine, right? It's less than 5%, less than 1% actually, and so it's just fine. We're almost done. X is defined by us. We need the concentrations that are relevant in the end, not X, so we want to plug our X back in and get our result. Right, N2O4 0.129 minus X over 2 is very, very much the same as 0.129. And for the NO2, we want to make sure that we're saying, well, we said it was equal to X. Let's explicitly say what its concentration is. We're being asked to solve for the equilibrium concentrations, and here they are. Okay, just as an aside, right, there is some flexibility how you define your ice table because I think that it is more tempting in a way to define it this way, minus X and plus 2X. And just quickly going through this gets us to the exact same answer even though we don't get the same answer for X. We still solve, we still do our 5% rule. Make sure that you're carrying that square in the numerator. It's 2X quantity squared, not 2X squared, that's 4X squared. We get the following, and we solve for X, and we get a different value for X. It's 0.00058 because we defined X differently. And this is why it's so important to go back in and plug your X's in for your final concentrations, because when we do, we see that our final concentrations are indeed exactly the same, right? While X is half the size here, that's because we defined it as such. The concentration of NO2 at equilibrium is 2X, which is the same answer that we got before. No matter how we define X, we should get that same answer. So X can be defined in any number of ways. some more sensible than others. There's no reason you can't say minus 100x plus 200x. They just have to be in ratio, and as long as you do them properly and take the time to say what the actual equilibrium concentration is in the end, they all can work. Okay, one last question here. Let's try this question. Calculate the number of moles of HI at equilibrium with the following at 448 degrees Celsius. So go ahead and pause here and try to solve this one. And my first question I'd ask you is, do we even need an ice table? Why or why not? And then go ahead and solve. All right, is this an ice table problem? This time it's actually no, right? And the key phrase here is that we are at equilibrium. There's no change to get to equilibrium, and therefore no relevancy for an ice table. Here, it's saying calculate the moles that are at equilibrium. Here's Kc equals all these, and these should say equilibrium concentrations. And we pretty much have K, and we have two of the equilibrium concentrations. We just need the third. We're simply solving for HI, and we get the following. So keep this in mind, right? Not every table is an ice table problem, or not every problem is an ice table problem. You want to direct yourself to an ice table when you are making a change to equilibrium. And if you're not making a change to equilibrium, for example, if you are already at equilibrium in the most likely sense, then you're not solving through an ice table, you're solving through some other means, and interpreting the problems correctly is really essential to solving equilibrium problems.